Download this code from codegive.com, link in the description below. Surrogate optimization is an efficient method used for optimizing expensive black box functions, which are functions that are costly to evaluate and may not have known gradients. The surrogate model acts as a proxy to approximate the actual objective function, allowing for fewer evaluations of the objective function while still finding an optimal solution. One popular approach for surrogate optimization is the use of Gaussian processes, GP. In this tutorial, we will explore surrogate optimization using a Gaussian process in Python. Step 1. Install required libraries. Make sure you have the following libraries installed. Bash. Pip install numpy scipy matplotlib scikit-learn. Step 2. Import libraries. Python. Import numpy as np. Import matplotlib.pyplot as plt. From scipy.optimize import minimize. From scikit-learn.gaussian_process import gaussianprocessregressor. From scikit-learn_process.kernels import rbf, constant kernel as c. Step 3. Define the objective function. We will define a simple objective function to optimize. For example, let's say we want to minimize the following function. \f x equals x 2 \2 3x Python. Def objective underscore function x. Return x 2 np.sin 3 x. Step 4. Create the surrogate model. We will use a Gaussian process to model the objective function. The Gaussian process will be trained on a set of sampled points. Python. Define the kernel. Kernel equals c 1.0 1 times 10 to the power of -3 1 times 10 cubed asterisk rbf length underscore scale equals 1 length underscore scale underscore bounds equals 1 times 10 to the power of -2 1 times 10 squared. Create the Gaussian process regressor. GP equals Gaussian process regressor, kernel equals kernel, n underscore restarts underscore optimizer equals 10. Step 5. Optimize using the surrogate model. We will iteratively sample points, fit the surrogate model, and use an acquisition function to find the next point to sample. Python. Def acquisition underscore function, x, gp. Expected improvement. Mean, std equals gp.predict, x.reshape, -1, 1, return underscore std equals true. Best underscore value equals np.min, gp.y underscore train underscore. Improvement equals mean, best underscore value. Return improvement slash, std plus 1 times 10 to the power of -6, avoid division by 0. Initialize sample points. X underscore init equals np.array, 0, 1, 3, 4, 5. Y underscore init equals objective underscore function, x underscore init, dot reshape, -1, 1. Fit the Gaussian process. gp.fit, x underscore init, y underscore init. Optimization loop. N underscore iterations equals 10. For I in range, n underscore iterations. Find the next sample. X underscore next equals np.linspace, 0, 5, 1000. Ec underscore values equals acquisition underscore function, x underscore next, gp. Find the point with the maximum acquisition value. X underscore max equals x underscore next np.argmax, ec underscore values. Evaluate the objective function. Y underscore next equals objective underscore function, x_max. Add the new sample to the training set. x_init equals np.vstack, x_init, x_max. y_init equals np.vstack, y_init, y_next. Refit the Gaussian process. gp.fit, x_init, y_init. Step 6, visualize the results. We can visualize the surrogate model, the objective function, and the sampled points. Python. Create a grid for plotting. x_plot equals np.linspace, 0, 5, 1000, .reshape, -1, 1. y_plot equals objective_function, x_plot. Predict using the GP. y_gp_mean, y_gp_std equals gp.predict, x_plot, return _std equals true. Plotting. plt.figure, fig size equals 10, 5. plt.plot, x_plot, y_plot, r, label equals objective function. plt.plot, x_plot, y_gp_mean, b, label equals surrogate model mean. plt.fill_between, x_plot.flatten. y_gp_mean.flatten, 1.96 y_gp_std.flatten. y_gp_mean.flatten, plus 1.96 y_gp_std.flatten. Alpha equals 0.2, color equals blue, label equals 95% confidence interval. plt.scatter, x_init, y_init, color equals black, label equals samples. plt.title, surrogate optimization using Gaussian process. plt.slabel, x. plt.elabel, f, x. plt.legend. plt.show. Conclusion. In this tutorial, we have explored surrogate optimization using a Gaussian process. The process involves 1. Defining an objective function. 2. Creating a surrogate model, Gaussian process. 3. Iteratively sampling new points based on an acquisition function. 4. Visualizing the results. This method can be very effective for optimizing functions that are expensive to evaluate, allowing for efficient exploration of the search space. You can extend this example by experimenting with different acquisition functions or optimizing more complex objective functions.